Alright, so now that we know how to solve some exponential equations, I want to recall some of the word problems and the formulas we looked at earlier, and to show how we could solve these for the exponents, which we haven't done yet. Okay, so when we looked at the compound interest or the continuous compounding formula, we were always given a certain amount of money, or maybe trying to figure out how much money we would start with to end up with a certain amount. But these, now we're going to be able to do things a little differently. So if you look at this example, how long will it take? So we're trying to figure out an amount of time. Well, time is our exponent up here, or up here, okay, depending on the problem. So we're going to be solving for one of our exponents. So how long will it take an initial investment of $10,000 to grow, so this is our initial amount, to grow to $25,000, so now that's our future amount, with a rate of 6% compounded continuously. So we're going to be using this formula. So 25,000 equals 10,000, and then e to the 0.06 t. Alright, so the rules from the previous page said if we've got a base to a power, we need to isolate the base. So right now it's being multiplied by a 10,000. So we need to divide both sides by 10,000. So 25,000 times 10,000, well, 25 times, or divided by 10 is going to be 2.5, and then e to the 0.06 t. Now, I've got a base to a power equals a value. So I can rewrite this as a logarithm. This is a base e, so this is going to be a natural log. So 0.06t is equal to the natural log of 2.5. Once we've got this, this is now a calculator problem. We're just going to take the natural log of 2.5. So let me clear this out. Natural log 2.5 equals, okay, and then we're going to divide that by the 0.06 that's multiplying our t to get the t by itself. So we're going to divide by 0.06, and I get 15 we'll say 3. So 15.3 equals t. So the problem was, how long will it take an investment of 10,000 to turn into 25,000? Well, it's going to take over 15 years for that to happen. That money would just have to sit there. Okay? Look at the next one. 1,000 is invested at 8% compounded monthly. How long before you have 1,500? So we're going to end up, now I did not give a lot of space here. I'm going to start over here. I may have to do kind of two columns. So 1,500 equals, we're starting with 1,000. Now, this is compounded monthly, so this will be this formula. So 1 plus 0.08 divided by monthly is 12 to the 12t power. Okay, so we need to simplify this. I'm going to do two things. First off, we've got a base to a power. I don't really know what that base is, so we need to simplify that and figure out exactly what's going on in these parentheses. But we also need to get the base by itself. So I'm going to divide by this 1,000. So I'm going to divide by 1,000. So that's going to be 1.5 equals. Let's figure out what our base is. So clear. So 1 plus 0.08 divided by 12 is 1.00. I know I'm writing down a lot of things right here. Looks then looks like it's 6 repeating to the 12t power. All right. So to solve this, this is now a base to a power equals a value. I need to write this as a logarithm. The base of my logarithm will be the base of this exponential over here. So it's going to be the log base 1.006 repeating, that's my base, of 1.5 equals 12t. All right, so this, yes, I get it. That is a very, very odd base, but we've got the change of base formula that will do this for us. So I'm going to come over here now. 12t is equal to the log of 1.5. So log of 1.5, and then divided by the log of 1.00, and then it was just a bunch of sixes. So I'm going to get 61 point, what was that? 0.223. And then we're going to divide by 12. So divide by 12. And I get 5 point, let's call that 5.09. So T is 5.09. So it'll take you about 5 years to turn $1,000 into $1,500 at that interest rate. Okay, so those are some money problems. Let's take a look at the growth and decay problems that we looked at earlier. So this is the same problem we had earlier. We have a colony of bacteria growing at a certain rate. Okay, how long will it take for the population to reach 140 grams? So this is our initial amount, 90. We want to know how long before our future amount is 140. So 140 equals 90 e to the 0.05 t. So just like what we did with the money, we're going to divide by 90. So 140 divided by 90. So what looks like 1.5 repeating equals e to the 0.05 t. This is an e, a natural number, so we're going to take the natural log of the other side. So the natural log of 1.5 repeating equals 0.05 t. So I've got two steps. I'm going to do the natural log of this, which is in my calculator. So I can do the natural log, and then I can hit the answer button. And then we're going to divide by the 0.05, and that's our answer. So t equals 8.8. I think this is in days. So it'll take 8.8 days to go from 90 to 140. Okay? B says, what is the doubling time? Well, for doubling, if we have 90, it just means when are we going to have 180? So everything else is the same setup. Now, first thing I have to do is isolate my base. So I'm going to divide. Well, 180 divided by 90 is 2. That's not a coincidence. This is a doubling time, so this is what should happen. So 2 equals e to the 0.05 t. So we are going to take the natural log of 2. And then we're going to divide that by 0.05. So calculator, natural log of 2, parentheses, don't forget the parentheses there, divided by 0.05, and 13.9, we'll say. T equals 13.9 days. That's how long it'll take to double. Okay? Now, we've got one more problem. This one's a little tougher. Okay? It has to do with half-life. So the half-life, so we've got some radioactive material. The half-life of radium is 1,690 years. So this is T. This is an amount of time that it takes this stuff to shrink down to half its original amount. If 10 grams are present now, how much will be present in 50 years? Well, we've got a problem here. We know what the half-life is, but we don't know actually what the decay rate. We need K. We don't know how fast this stuff is like shrinking. We just know that it takes 1,690 years to go from its original amount down to half. So this is actually a two-part problem. It just doesn't look like it. Okay, you see one question mark, you're being asked one question, you don't realize it's a two-parter. The first thing we have to do is figure out the decay rate. So the half-life is 1,690 years. So using this formula, the amount that I start with, okay, that's what this is. I'm going to start with a certain amount. I am going to end up with half of that amount. That's what a half-life would be. Whatever I start with, I'm going to have half of that over a certain amount of time. E to the, and then I've got a K and a T. Well, the K is what I'm trying to solve for. I'm trying to figure out what that K is. How fast or how slow is this stuff decaying? And the amount of time that it takes to get half of our amount is 1,690. Now, I need to solve this. First thing we're going to do is we're going to notice that these two A's are going to cancel each other out. I've got an A on this side and an A on this side. If I divide both sides by A, they're going to cancel, and I'm going to have 1/2 E, and then I'm going to flip these around so it looks more normal to us, where we have the number first followed by the variable. That's it. Okay, I just need to do this, and this is now a calculator problem. Take the natural log of 1/2, divide it by 1,690, and that'll be our K value. So, natural log of 1/2 equals, and then divide it by 1,690, and I get negative 0.000. All right, I'm gonna put 41. Okay, after that there was another 0, so I'm kind of running out of like significant digits. Okay, you could write all those down if you wanted. Okay, but I'm going to write that down. So now we know our K, we know our decay rate. So now this problem over here is pretty easy. Okay, we've got 10 grams present now. So how much will be present in 50 years? So we want to know the amount that we're going to have in 50 years. This is function notation. This isn't something I'm going to solve and divide by 50 or anything. This is just a function notation. Over here, it's going to be my initial amount, which is 10, my e to the negative 0.00041 power times my time, and in this case it's a 50. So I just need to plug all that in my calculator, and that's my answer. The amount that I will have in 50 years is 10 e to the negative 0.00041 times 50, 9.797, we'll say 9.8. Okay, this stuff does not decay very fast. Okay, it takes 1,690 years to go from 10 grams to 5 grams, because that'd be a half amount. Okay, so in a mere 50 years, this stuff is not going to shrink down very much, so 9.8. So that's it. So take a look at your worksheet and let me know if you have any questions on solving the equations or on these word problems. All right, thanks.